Alright guys, so in this video we're going to take a little bit of a closer look at some special right triangles, and specifically we're going to look at their side lengths and how we can find their side lengths relative to one another. So the first one that we want to look at is an isosceles right triangle. Isosceles meaning that we've got these two congruent sides, and right triangle, obviously we've got this vertex angle up top that's equal to 90 degrees. So before we get into finding the measures of each side, we just want to look at the characteristics of this thing. And we know for any isosceles triangle that if it's isosceles, then it's got one pair of congruent sides, so the legs are congruent. But we also know that the base angles are going to be congruent here. So let's check out what exactly this means. These base angles are congruent. We know this is 90. Well, we know that the triangle sum theorem says that the sum of the triangles, or I'm sorry, the sum of the angles is going to be equal to 180. So if that's true, then we've got 180 is the total sum of the angles. We know that this vertex angle up top is taking up 90 of those total degrees, and so we've got 90 degrees left for the two base angles. Well, what does that mean? We know that these are congruent, and when we add them up, they're going to be equal to 90, so each one of these base angles is actually going to be equal to 45 degrees. We just chop 90 degrees in half, and we get 45 degrees. So that's going to be the degree of the base angle. So when we say isosceles right triangles, we're also referring to the special case, and it's a little bit more well known as a 45, 45, 90 triangle, and it's a specific reference to the angle measures. All right, so that's the first part. The second part is we want to find an expression for the measures of each side. So in doing that, what we're going to do a little bit of an informal proof. So first thing is we're going to let triangle ABC be a 45, 45, 90 triangle. All right, and we just talked about those characteristics. 45, 45, 90 triangle really just means that it's an isosceles right triangle. So both ways, you can state that both ways. So the next thing we're going to do is we're going to name one of these side lengths. Or not name it, I'm sorry. We're going to attach a variable to one of these side lengths so that we can show that no matter what the measure is, we've got a relationship between the side lengths. So let triangle ABC be a 45, 45, 90, and we want to let, let's start with AB, the side have a length of x. So this side has a length of x. Well, because this is an isosceles triangle, we also know that AC is going to be equal to x, and that's because it's isosceles. So if you want to call it something, it's really isosceles triangle theorem, or you can just say the definition of an isosceles triangle, at least two congruent sides. So if this one's x, then this one's also got to be x because it's isosceles. Now the next thing is going to make use of the fact that this is a right triangle, and one of the major tools that we have to deal with right triangles is Pythagorean theorem. So I know with Pythagorean theorem, with any right triangle, I can take one side length and I can square it, and I can add it to the other side length, and I can square it, and the sum of those two squares is going to be equal to the third side length, which happens to be the hypotenuse. So in this case, it's b squared. All right, so let's take these two lengths, add them together. We've got like terms here. Both are x squared terms, so we end up with 2x squared equals bc squared. And what I want to do is I want to isolate bc, so in order to do that, I've got to take the square root of both sides. When I take the square root of both sides, underneath this radical, this is going to simplify to BC, which is my hypotenuse. Over here, we can pull out an x. So we've got x, and then what's left is the square root of 2. All right, so what we just figured out is that this side length is always x times the square root of 2. Okay? So ultimately, big picture, what this means is if I know one of the side lengths, I've got this relationship where the ratios of their sides are going to be 1 to 1 up here. My two legs, the ratio is 1 to 1. It's always the same to the square root of 2. So if I know one of the sides, I can actually use these ratios and these relationships to figure out what the other sides are. And again, this is specific to a 45, 45, 90 triangle. All right, so let's look at a couple examples and see how this is useful. Here is an example. Find all the missing angle measures and sides for each. We want to leave our answer in simplest radical form. So here we've got an isosceles right triangle. Isosceles right triangle, which then tells me I've got angle measures that are 45, 45, 90. All right, so that property that we just figured out is going to apply here. So what I know is that one of my legs is 7. Well, if AB is 7, then AC is also got to be 7 because it's isosceles. All right, so if I know that one leg is 7, I know the other leg is 7. The other thing that I can figure out based on this last slide here that we did, I know that if I know this side is x, then this is just going to be that measure times root 2. And we just proved that. All right, so whatever the measure of the leg is, BC, that side, is going to equal AB, the length of this, or AC, either one, times root 2. And we know that AB is 7, so BC is going to be equal to 7 root 2. And we can just leave it in that form there. One more example using this 45, 45, 90 rule. Again, we've got an isosceles right triangle. And that tells me I've got a 45, 45, 90. So I can use that relationship. This one's a little bit tougher because we kind of have to work backwards. Remember, the relationship says if you know one of the legs, then it's going to be, then the measure of the hypotenuse is just the measure of that leg times square root of 2. Here we've got to go backwards. So using that relationship, if we call this x, we know that this, BC, the hypotenuse, is going to be x times the square root of 2. So in order to solve this, we've got to solve for x, divide by root 2, divide by root 2. And thinking back to Algebra 1, or just our basic algebra principles when we're dealing with square roots, we know we can't have a square root in the denominator. So I've got to take this, make sure that I rationalize, get that square root out of the denominator, and in order to do that, I need to multiply by root 2 over root 2. So this is my x, or just the measure of AB and AC. So I'm left with 6 root 2 over root 2 times root 2 is just 2. And in order to simplify this, that's going to cancel, and we're going to get 3 times root 2. So I can go back up here. I know that AB is the same as AC, which is equal to 3 root 2.